This module will introduce you to concepts of stability, redundancy, and fatigue. These are crucial to the safe and reliable function of bridges. What is presented here is the tip of a very burly yet lovely iceberg.
Truss bridge stability is a very important topic because we want to have the truss perform as was designed, and that means the truss elements being vertical. And so you're going to see a lot of bracing on the top just to make sure that those trusses stay parallel to each other and stay vertical. So there's quite a bit of bracing in there. It's called secondary bracing, but it is very important to all those parts are oriented as they were designed.
And then for lateral forces, there's sway frames at all the intermediate panels, and then the portal frames themselves are heavily braced. And the sway frames and the portal bracing do is they allow the truss to collect all the lateral forces from wind and earthquakes and so forth, and then collect them at the end posts of the truss. And then the end posts are sized in a way that they can carry the forces down to the bottom by bending.
Trusses are three-dimensional systems, though we often think of them as two-dimensional. In the Van Buren Bridge, the vertical trusses do the heavy lifting. However, if they weren't laced together with horizontal bracing, they would simply tip over. With horizontal bracing, the truss remains stable for vertical loads and can withstand lateral forces. In the new bridge, the girders are stabilized by cross frames and concrete deck, which is attached by headed shear studs. These keep the beams from rolling over and transmit lateral wind and seismic forces into the substructure.
Redundancy is important because Murphy's Law is something we need to take heed of. If something goes wrong, then redundancy gives you a way to not have catastrophe. And in the case of the bridge, that would be like collapse or partial collapse or something close to it. So in 1913, as far as I know, it wasn't a serious consideration. Actually, I believe the bridge industry has followed other industries like aviation. You'll see in World War II B-17 bombers that came back with, half the tail missing and big, huge holes in the wings and fuselage and different things. Turns out that the way that particular airplane was built had a tremendous amount of internal redundancy. I think it was a happy accident probably at the time, but since then, that industry has gone in and sort of had the light bulb go on and actually institutionalized. They actually do what's called damage tolerance analysis. It's not just by chance now, they're planning, for, okay, what if any particular piece of structure fails, how does the airplane get home? And so now fast forward to the last 10 or 15 years, the bridge industry has adopted a philosophy like that. Not quite as rigorous, but it's in the ballpark.
Redundancy can be designed into a bridge with for example, a new Van Buren Bridge with having multiple girder lines. So
if it's more than two,
we're calling it redundant, because that way if one girder fails, the other ones can carry the load, and then the bridge can be closed and made safe again to use. So that's so load path redundancy there, and also the system redundancy of just having the steel girders go all the way across the river, supported in multiple internal locations, so that if one part fails, that girder line will actually help hold the bridge up. But it's interesting how that will just work structurally, because if you put a load on that first span, the rest of that steel girder is going to bend a little bit, even the spans that aren't loaded. And so if you have a failure in one of those girders, you're going to have 4 other girders that can take that load, but also the remainder of that girder is also still there. So that's kind of abstract look at redundancy, but that's one type of redundancy the new Van Buren Bridge will have.
The AASHTO LRFD bridge design specifications require that multiple load path and continuous structures should be used unless there are compelling reasons not to use them. Redundancy can come from 3 ways. 1, load path. 2, system. And 3, internal.
Load path redundancy is achieved when an alternate and sufficient load path exists. Typically designed and detailed structures allow for a level of load path redundancy that enables the structural system to carry loads after damage to or the failure of one or more of its members. These details include the use of multiple girder lines and continuous decks connecting the girders.
System redundancy can be achieved by continuous beams over interior supports or other three-dimensional force transfer mechanisms, such as cross frames. System redundancy must have adequate capacity to carry loads in a damaged state. Internal redundancy exists in bolted or riveted, built-up member. If a crack propagated through the middle plate of this member, there is a high probability it wouldn't propagate into the other elements. The angles and top plate could still carry substantial force. Recent experimental and analytical studies show redundancy can exist in bridges when considered as a three-dimensional system. This gives engineers the ability to look deeper at the reliability of bridges previously thought to be non-redundant. This can be advantageous given the cost, disruption, and environmental impacts of replacing existing bridges.
Fatigue is when a bridge is loaded at a level below what the yield strength is. Like it's not loaded that heavily, but it's loaded many times. Like when a truck goes over a bridge, there's going to be vibration, and there can be thousands of trucks go over a bridge. So you might get a small crack, and that crack, for its majority of its life, is going to be really small. You're not even going to see it. In fact, it might be under the rivet head or under the bolt head, and then it can propagate, just get a little bit bigger. The life of a crack spends most of its time being very small. Fatigue is critical for bridge design and fabrication. We're talking about just steel bridges, because these bridges are going to see thousands of loads over their lifetime. And if there's a poor detail, or if there's the steel itself isn't all that tough, then you can have a small crack that gets formed. And on a major structure, we look at those every 2 years, but the steel's going to have a layer of paint on it, and that crack could be under a rivet head, it could be under a layer of paint.
ASTM E1823 defines fatigue as the process of progressive, localized, permanent structural change occurring in a material subjected to conditions that produce fluctuating stresses and strains at some point or points, and that may culminate in cracks or complete fracture after a sufficient number of fluctuations. Pulling key words from this definition, we see 1. Progressive, 2. Localized, 3. Permanent, 4. Fluctuating stress and strain, 5. Cracks, and 6. Fracture. Fatigue crack growth has 4 primary stages. 1. Nucleation, when no crack exists, but micromechanical changes occur that lead to a crack. 2. Short crack growth, where the crack path and growth rate is highly dependent on local grain and environmental conditions. 3. Long crack growth, where the crack is defined by smooth growth, often perpendicular to principal tension stresses. And 4. Final instability, when the crack growth advances at the speed of sound in the material, often leading to complete fracture. For fatigue, AASHTO requires that the live load stress range delta F be lower than the nominal fatigue resistance delta F sub n. The nominal fatigue resistance is equal to the fatigue threshold for infinite life, or the following equation for finite life. Keep in mind, infinite life is defined as 75 years. The AASHTO LRFD bridge design specifications provides values for the fatigue constant and threshold for various structural details. These details are divided into 5 categories depending on their susceptibility to fatigue. The variables that influence fatigue life are many, and their interactions can be quite complex in cases, as seen in this flowchart. Manufacturing, load effects, corrosion, and wear are some of the dominant variables in fatigue life. William Pellini, the superintendent of the Naval Research Lab's Metallurgy Division, said decades ago, "Present trends in fracture research emphasize an ever-increasing sophistication in the treatment of the problem, building upon rather than eliminating past knowledge. Therefore, the engineer should not expect that fracture-safe design should ultimately evolve to a single generalized procedure, but rather to a variety of procedures that overlap and integrate into a coherent pattern. This statement is still true today. Embrace the complexity. To address the reality that bridges sometimes crack, corrode, or are otherwise damaged, federal law requires bridge inspection to find damage that may inhibit a structure's ability to perform as intended. The Bridge Inspector's Reference Manual, jointly published by the Federal Highway Administration and National Highway Institute, is a thorough reference on how to inspect bridges of any type. It covers many damage mechanisms. When visual inspection isn't sufficient, advanced inspection techniques are required. These include acoustic emission, crack propagation gauge, dye penetrant, eddy current, magnetic particle, magnetic flux leakage, ultrasonic, and phased array ultrasonic. An alternative to the safe and infinite life design methodologies is fracture mechanics-based design and evaluation. This is a robust analytical and experimental tool that provides engineers the ability to assess an assumed crack in design or an actual crack in the field. The Federal Highway Administration and National Highway Institute have published the Design and Evaluation of Steel Bridges for Fatigue and Fracture, which contains a solid primer on this topic. The fundamental fracture mechanics relationship indicates when the stress intensity factor equals the fracture toughness, and unstable crack growth will occur. The stress intensity factor is a function of a far-field stress and crack geometry. Engineers use handbooks and finite element software to solve these. Fracture toughness is a function of elastic modulus and surface tension. The latter is difficult to obtain. However, testing with specimens like this provide fracture toughness.
Looking at the specific case of a semicircular edge crack, the Mode 1 stress intensity factor is given by this equation, where F is the far-field stress, A, the crack depth, Q, a geometry and stress adjustment factor, Phi, a shape factor, F sub y, the yield tensile stress, and C, half crack length. Let's look briefly at three key fracture toughness realities. First, size. For common structures, as member size increases, fracture toughness typically decreases. This is also true for strength, stiffness, and stability. Fracture toughness typically decreases as material thickness increases. For thicker materials, a plane strain condition may exist. The constraint condition is influenced by both material thickness and crack geometry.
Second, temperature. In steels, as temperature decreases, fracture toughness decreases. The large drop in toughness is the nil ductility temperature. As temperatures below this point ordinarily ductile still will behave in brittle fashion. Third, test matters. The left curve is from the Sharpie test, and the right from a dynamic tear test from a failed structure that surprised many engineers. The design was based on Sharpie, which underpredicted the true transition temperature. Specimen type, size, and notch preparation matter tremendously. Utilizing fracture mechanics-based crack growth data, we can plot crack growth rate dAdN on the vertical axis and stress intensity factor range on the horizontal. The left region is the small crack growth regime and hard to predict, as it is highly dependent on grain and residual stresses. The right region is unstable growth regime and is also difficult to reliably predict. Therefore, engineers focus on the middle, long crack regime. They do this by setting the left delta K by inspection thresholds and right delta K by the critical crack size. Integrating between these two limits provide an estimate on fatigue life. Often, the test data in the stable crack growth regime is linear on a log scale, and life can be calculated as the area under this portion of the curve. This module has introduced you to fundamental concepts in structural stability, redundancy, and fatigue. An engineer can spend decades studying and understanding each of these topics. And indeed, many experts exist in these areas and are worth consulting on complex, challenging problems.